class. This is chapter 14, lesson 1. We're looking at regular polygons. Okay, so when I talk about regular polygons versus irregular polygons, there's a very specific definition for what makes something regular. So it says here, a regular polygon is a convex polygon, so that's opposed to concave. Remember we looked at pictures of if something went in like that. That would be concave. It caves in. Okay, so these all have to be convex, nothing caving in anywhere. And it has to be both equilateral and equiangular. Okay, equilateral and equiangular. So like these photographs of snowflakes under a microscope, these are regular polygons because we see all of their sides and angles are the same. Okay, so we can look at the first 8 regular polygons here. So note that, like if you think of a quadrilateral, okay, a rectangle might seem like, yeah, that's a regular polygon. That's one of those things you learn in kindergarten or preschool, or maybe when you're 2. I don't know. There's a lot of block sets with rectangles and stuff in them. They're a pretty standard figure, but they are not regular. Because think the sides can vary in length to each other. You could have a long skinny rectangle or a rectangle that's just slightly off from being a square. So a square is the only regular quadrilateral, okay? Just like an equilateral triangle is the only regular triangle, okay? And then you have pentagons, hexagons, heptagons, octagons, nonagons, that's 9 sides, and decagons, that's 10 sides. So they have to be both equilateral and equiangular in order to be classified as a regular polygon. Now, notice that as the number of sides of a regular polygon increases, it looks more and more like a circle, which is because every polygon is cyclic. Okay, we talked about cyclic figures in previous chapters. We said that in chapter 12 and 13, for example, that if the opposite angles of a quadrilateral are supplementary, then it is cyclic. We said that every triangle is cyclic. And that just means that it can be inscribed within a circle, okay? As we see in this regular pentagon here. Inscribed in a circle, meaning that all of its vertices lie on the circle, okay? So every regular polygon would be cyclic. Now, you can think of this in terms, and we know that all triangles, not just the regular ones, are cyclic. In our square, all of our angles are 90 degrees, so we know that our opposite angles are always going to be supplementary. Okay, so that would fit the definition of a quadrilateral being cyclic. But why do we know that the other ones are cyclic? Okay, well, surprise, surprise, even in this chapter on other types of polygons and circles, we are still going to involve triangles again, and all the things that we know about triangles. And so we're going to take these figures and divide them into triangles. And it turns out, I mean, if you think of with any of these, I can draw triangles and divide any of these figures up with little triangles, okay? So you can see how you could go from the center to the vertices and draw lines, and you're going to get triangles, okay? All of your regular polygons are going to be able to be divided up into triangles, okay? And then we can use the relationships in those triangles to prove that every regular polygon is indeed cyclic, okay? So we can see here, as we've drawn here, we use the same terminology in a regular polygon as we do in a circle and call this distance the radius. So you can see that it's the radius of this circle. It's going from the center to the edge of the circle. But this line that's going from the center to the vertex of the polygon is also called the radius. Okay, so it's the same for both. So you can see that we have these radii, all of which are equal because we know that all radii are equal. We have these radii there going from the center of the polygon to the vertex, which is also going to the circle. Okay, and for it to be cyclic, we need all of these vertices to lie on there. Well, we can prove this just using congruent triangles. Okay, it's fairly easy to show that we have congruent triangles all around. For one, we know that these radii are equal. Okay, so I have sides of the triangle that are equal there. Okay, I know that my regular polygon, if it is regular, it not only has to be equilateral, meaning these sides are equal and these radii are equal. So I have side, side, side. Oh, well, that's really enough, isn't it? We could get into angles because every regular polygon must also be equiangular. But we really have enough because we know that the radii are equal, and I know that the sides of the polygon must be equal if it's equiangular, to know that I have side, side, side congruence here. Okay, so given that, we can also, if you want to include your angles as well, these all, 1 plus 3 has to be equal to 2 plus 4. I know that 1 and 2 are equal because this is an isosceles triangle, so the opposite angles are equal. So by subtraction, 3 and 4 must also be equal. Okay, so if 1 plus 3 is equal to 2 plus 4, because that's an angle of the pentagon, that's an angle of the pentagon, it's equiangular. And 1 and 2 are equal because these sides are equal. So it's an isosceles triangle. Those sides have to be equal, those angles have to be equal. Then I can subtract 1 from 1 and 3, 2 from 2 and 4, and so 3 and 4 must be left to be equal. Okay, so I have equal angles and equal sides in these triangles, so I know I have congruent triangles all around. So I can continue to go on and draw like OE here. I can show that, okay, I already know that this is a radius of the circle and the pentagon. This is a radius of the circle and the pentagon going around. If I know that everything is equiangular and equilateral in here, then OD is going to be the same length as OC, right? And so OD should also be a radius of the circle. Okay, I can go ahead and continue that around and show that this triangle then is congruent to the others, and so OE must be the same length also, and so it would also form a radius of the circle. Okay, so you can see how we can then see that the polygon is cyclic. And because all of our regular polygons can be broken down into triangles, one that lets us show this by the same method that every regular polygon is cyclic. But it's really helpful in other ways because we know a lot about triangles. If you haven't noticed by this point in the year, we have learned so much about triangles. And so for any figure that I can break down into component triangles, I can then find out a lot of information about it. And one important thing to find out about it would be its area. Okay, because if you think about it, if I just said to you, what's the formula for the area of a regular octagon? You might look at me and say, were we supposed to have learned that yet? No, that's not one of those formulas we just learned. We learn triangle area formulas. We learn square and rectangle area formulas, but there's not a simple formula that we've picked up along the way for our larger regular polygons. And it turns out that the best way to do that is by breaking it down into triangles and then multiplying by the number of triangles. It really is. So we're going to look at that over the next couple of lessons and then look at how we were able to go from there, using what we know about triangles to help us find out more about other polygons, and then how we could go one step further to say, well, if I know this now about a regular polygon, could I now use this to help me find the area of a circle? Something which was much harder in the ancient world because they didn't have pi r squared yet. So we're going to look at how pi r squared came to be as a formula, how Archimedes discovered that, and how it relates back even to our beloved triangles. Okay, I'll show you one more thing for this lesson. Okay, just a couple of words here, and we should know most of them, okay? This is still the center. This is still a central angle, just like we had in the previous chapter. That's a central angle of the regular polygon, just like we had a central angle of a circle. This distance from the center to the vertex is still the radius. But then this is our new one. Okay, so if you draw a line straight down from the center to the side, not to the vertex, but straight down to the side, that is called the apothem. We'll use that in the next lesson. Okay? So an apothem is just a perpendicular line segment from its center to one of its sides. Okay, that's it for lesson 1. I'll see you back at lesson 2.